All right, excellent. In the previous lesson, we learned how to plot data on a graph. As expected, now we will run a regression and will then focus on the interpretation of some statistics that can be obtained after running the regression. The Stats Models module contains tools for running a regression. The procedure to follow needs you to include a constant. We will assign the newly obtained information, which is the object x, and the constant to a new variable. Let's call it x1. Right after that, we will assign to another variable, reg, the output of an ordinary least squares regression, OLS. As arguments, we must add the dependent variable y and the newly defined x1. And at the end, we will need the fit method, which you can think of as a method that will apply a specific estimation technique to obtain the full fit of the model. Finally, reg.summary will display the OLS regression results and will organize them in 3 tables. As you can see, we have many statistics in front of us. This is great, but we have to prioritize and will not focus on all of them. At the top, we always see the name of the dependent variable and the type of regression we have run. In our case, we are trying to explain house price levels, and the method we are using is least squares, hence the name of the model, OLS, standing for ordinary least squares. The R-squared value we talked about is shown in the top right corner. 0.678 means that the independent variable in our regression, house size, can explain 68% of the dependent variable, house price. This value is a lot greater than 30%, so we can affirm our model has good explanatory power. Thus, it is a good model. House prices are, in fact, explained largely by house sizes. The next table is the one we are interested in the most. The first row contains results regarding the constant we added. Sometimes, Python provides the results in scientific notation. This is the case for the number of the obtained coefficient. Anyway, it equals approximately 260,800, and this is our alpha. In fact, it is also the intercept in our regression. This means when we draw the regression line, the starting point of that line on the y-axis will be 260,800. All right, let's move on to the next row. How should we interpret the obtained coefficient of $402? It means that for every square foot increase of the size of a house, its price is expected to rise by $402. Namely, this coefficient is the value of beta in our regression equation, or the slope of the regression line. On the other hand, the standard error of $65 tells you this augmentation of $402 will typically vary within a range of $65. Let's see if this logic is correct. Per our regression output, which relies on the classical OLS regression equation, we can expect a house with a size of 1,000 square feet to equal alpha, which is $260,800, plus beta, which is equal to $402 times 1,000. The output of the equation as constructed is given by $662,800. When we go back to the graph we created in our previous Python lecture, we see there are two 1,000 square feet houses whose prices are only slightly lower than the one we predicted, $662,800. Therefore, our prediction fits well with the actual data. Before we finish this lecture, a note on Python. The Stats Models library allows us to apply a complete OLS model that provides 3 tables with multiple statistics. Alternatively, SciPy's linRegress allows us to extract 5 of these statistics very quickly. The slope, beta, the intercept, alpha, the R value, the p-value we will soon introduce to you, and the standard error. In addition, the values are floats and are readily available for further calculations. Please don't forget to raise the R value to the power of 2 to obtain the well-known R-squared statistic. The other values are the same as the one we saw in the earlier regression output, right? The slope is $402. The intercept, around $260,800. And the standard error, $65. We will learn about the p-value in the lesson where we introduce multivariate regressions. The exercise attached to this lecture is very interesting. You will need to manipulate some of the 5 statistics obtained with LinRegress to solve it. Good luck, and thanks for watching.